Yeah, so my talk will be about graph norms. So there are two papers in archive, one with Bjarne Schülke, who's a student in Hamburg, and the other is with Frederik Garbe and Hladký from Prague. Yeah, but so I did a couple of talks with the same title and same abstract, and it turns out that I might have been too ambitious when I wrote the abstract. So to explain like everything in the two papers. I mean, the two papers are both quite short, like 10 pages, but still, yeah, I might have been too ambitious. So this time I would focus on the work with Bjarne. Yeah, if time allows, I expect not, but if time allows, then I would explain something about the result with Frederik and Jan too. Yeah, so first thing first. So let me start by defining the graph homomorphism. So graph homomorphism is a vertex map, which means the map between two vertex sets of two graphs that preserves adjacency, which means whenever my UV is an edge in H, my FU and FV is an edge. And it's not necessarily injective. We allow some degeneracy, which means the two distinct vertices can be mapped to just one single vertex. Okay, so that's the definition of graph homomorphism. And the graph homomorphism density TH of G is defined as follows. So this is a set of all homomorphisms from H to G, and I divide the number of whole homomorphisms by all possible, the number of all possible vertex maps. Okay, and there are a couple of ways to rephrase this definition, which is firstly the following. So I take some probability, so which means I consider some random vertices, uniformly random, from the whole vertex set of G. So I take that many independent random vertices to embed my vertices in H. And I look at the probability that those two, so XU and XV are the independent random vertices, where U and V are corresponding the vertices in H. So I look at the probability that those two are adjacent whenever my UV is an edge in H. So these two are adjacent in G. So yeah, because by sampling these vertices uniformly random independently, I just take a uniform random vertex map, and I look at the probability that it becomes a homomorphism. Okay, so you agree with this rephrase? Yeah. And then, because probability is naturally rewritten with expectation of an indicator function of an event, I can rephrase this as follows. So the indicator is obviously this guy over here in G, and I take a product of these indicators because I want them all to be 1, right? So, sorry, this is H. Okay. And yeah, so in a matrix sense, I look at some function, basically, on the set of vertices, which is 0 and 1. So 0 if there's non-edge, and 1 if there's an edge. And I take a product on which is indexed by these guys. So if I rewrite this a little bit, I mean, I consider some relaxation of this product, then I can extend the definition for any two variable functions, which is the following. So I basically replace my G to a two variable function, which is symmetric from 0, 1 squared to either 0, 1 or even to R. So this is symmetric. I get this expression. So if my W is just the indicator function of G, then I get exactly this. Well, you might worry about the domain of this function, but you can always chop up your square into equal pieces, and you put some zeros and ones according to your adjacency matrix, basically. Yeah, then you get a step function. Okay? Yeah, so this is how to relax your definition of graph homomorphism density in this graph limit setting, if you know about the theory. Okay, then the question I'm concerned with in this talk is the following. So here's some possibly large product of functions, and I take an average, which is reminiscent of the definition of LP norm you learn in the functional analysis. So what I'm going to do is the following. If I take the absolute value and take the exponent of 1 over the number of edges in H, yeah, I mean, this is exactly the number of functions in this product, right? So I just want to scale it down in a correct way. Yeah, so if this is a semi-norm, or whether I mean, in the definition of LP, we also take the absolute value inside the average. So I can also do this is a norm. So just in case you forgot the definition of norms, let me give the definition. So this is some function f is a norm on the vector space V if the following three conditions hold. Firstly, fx is 0 if and only if x is 0, and f lambda x is 0. F lambda x is equal to the absolute value of lambda times f of x. Yeah, that's basically why I take this exponent. Yeah, and the subadditivity. So f of x plus y is less than f of x plus f of y. This is a triangle inequality. Okay. Yes. So, and it's a semi-norm is when only this direction holds. Yeah. So this actually follows from this. If you put 0, then you get 0. So it should be 0. Yeah. But the converse is something where we should assume. Yeah. So if only this direction, which follows from this guy, holds, then we say that it's a semi-norm. Yeah. So this is a question, and you might just wonder why on earth do we care about this problem? Yeah, so probably the quickest and the most mundane answer for that is the question is asked by Lovas. Yeah, well, this might not be a very good answer. So let me explain some other reasons to study these questions. So firstly, it connects to the quasi randomness. So quasi randomness is the definition for some large graphs to be like random-like. So there are a couple of ways. There are quite a few ways to define this. And for me, the most natural way to define quasi randomness for large graph, by large graphs, I mean I'm basically in a very rigorous way, I'm thinking about some graph sequence with like growing number of vertices. Yeah, but I'm just pretending it's just a large one graph. yeah, so the quasi-randomness is the following, basically. I have some graph sequence. Yeah, let me be rigorous. There's some graph sequence where my number of vertices goes to infinity, and say my edge density goes to p for some fixed value p. And my sequence of graphs is so-called quasi-random if my h count for any fixed h, my h count in my GN converges to what I expect in the random graph. So, yeah, if you think about the Erdős-Renyi random graph, you just flip a coin for every edge. So you sample vertices first, and then you flip a coin for every pair that exists in H. Then you get exactly this probability that your sampled vertex map becomes a homomorphism, right? Yeah, so it's the mean of the expectation. The mean of the expectation. That's a crappy expression. Yeah. So in random graphs, the th of GNP is concentrated around this value. Yeah, and what I expect for this quasi-random is somewhat random-like, so it converges to here. So if I define like this, then one surprising fact by Chong, Graham, and Wilson, and by Andrew Thomason in late 80s states the following. It's just enough to check one graph. For example, if I take this guy, the full cycle, and then if this converges to p to the 4, then it's actually equivalent. Yeah. Which is, I mean, at first glance, it sounds quite surprising. And what's more surprising is that we can actually replace this C4 by any even cycle. Yeah. So, yeah, so if such thing happens, so if some TF of GN converges to P to the EF, forces every H density to converge to what we expect in the random graph, then we say that my F is forcing. Okay, for example, even cycles are forcing. And the famous conjecture in this area says that any bipartite graph, so it must be bipartite, so that's not hard to check, but anyway, every bipartite graph with a cycle, any cycle, is forcing. So that's so-called forcing conjecture. Forcing conjecture. Any bipartite graph, not a forest. F with a cycle is forcing. Which is a major open problem in this area. And in particular, if this is a norm, so let me just define some notions. So I'm going to say that my H is semi-norming or just norming if this defines a semi-norm or norm, respectively. And if this is a norm, then I'm going to say that it's weakly norming. And as the name suggests, this is weaker property, which means if a graph is semi-norming, then it's weakly norming. So it's not that easy to see right away, but it's not hard to see. You'll see in half an hour, say, hopefully. Yeah. Okay. So that's, yes. And one application of this property is that if a weakly norming graph, which is a weakest property along this line, weakly norming property, weakly norming F with a cycle is forcing. Yeah, so this is a fact. Any weakly norming graph with a cycle is forcing. With a, yeah. Any weakly norming graph F with, sorry for crappy handwriting. Yeah, so any weakly norming graph with a cycle is forcing.
Weakly norming graphs are all bipartite?
Yes. Yeah. Yeah, you will see that in a minute too. And yeah, let me just remark one little thing. So you could just see that, well, this is not very hard to prove, at least for this property, because here you're averaging some non-negative function, and if it's 0, then it must be 0 almost everywhere. Yeah, basically. So this property here is kind of obvious, and the second property is also obvious. I mean, I kind of cooked up the exponent in such a way that this just works. Yeah, so what I mean is the whole difficulty lies in this triangle inequality. If I have triangle inequality, then I'm done. Yeah, so this is basically, so I'm interested in other words, I'm interested in proving triangle inequality. Okay? Okay, so this is the first application of the result, which makes it a little more interesting. And the second one is Sidorenko's conjecture. So it's another major open problem in extreme of graph theory. And actually, forcing conjectures implies this conjecture, which is the following. So the Sidorenko's conjecture, which is also conjectured by Erdős and Simonovitz in a slightly different form, but it's kind of equivalent when your G is dense. So for any H, for any bipartite H, and for any graph G, this inequality holds. It's a beautiful statement, you know. It's just very simple and still open. So any bipartite graph H, and the bipartiteness of H is totally necessary, because if you put, say, a triangle here, and you consider some dense bipartite graph, say complete bipartite graph, then you have 0 triangle density for obvious reason, whereas on the right-hand side, you have some positive quantity, because your complete bipartite graph has density half, roughly. Okay? Yeah. So the bipartiteness, and by the same reason, for any non-bipartite graph, you can take complete bipartite graph, and then you have 0 density, whereas you have positive density. Okay? So bipartiteness is really necessary. Yeah. So you all agree? Yeah. Yeah. And for any G, if such inequality holds, then I'm going to say that H is Sidorenko, if this inequality holds for any G. There are lots of Sidorenko graphs, which I wouldn't mention. Yeah, there are lots of results, but let me just briefly mention the fact, another fact. Any weakly norming graph H is Sidorenko, which is another application to some similar problem, but yeah. And I should also remark that the converse doesn't hold. So there are known Sidorenko graphs that are not weakly norming, so which I'm gonna talk in 10 minutes. I'm just making too many appointments. Yeah, but yeah, so this is the case, and this is another motivation to study this question. Okay, so if it sounds interesting enough for you, then I would move on to some progress on this question. Okay, so what's known? What's known?
So the weakly doesn't imply forcing. You have to have a cycle.
Yeah, there should be a cycle, but it's actually any weakly norming graph that doesn't contain a cycle is just a disjoint union of stars. So it has really strong structural property. So disjoint union of isomorphic stars, actually. Yeah, even stronger. Yeah, yeah, yeah. Proving star being Zelenko is kind of like easiest exercise. Yeah, yeah. I mean, yeah, it really is. Yeah, just apply some Jensen's inequality, then you're done. Yeah, it's like 5-minute exercise. Yeah, yeah. Okay, so let me tell you about what's known. So firstly, the first in-depth study of this question was done by Hatami. So what Hatami proved is the following. So let me firstly mention that there's some subtle technicalities with these semi-norming and norming properties. So in this talk, let me just focus on this weak norming property. But there's good probability, like high probability, that there's some corresponding statements for norming graphs. Okay, so let me just focus on this, and if you want to know whether there's a corresponding analog for these guys, then you could just stop. Yeah, whenever you want to ask, you can just stop my talk and just ask the question, then I would say just yes and no. Yeah, so what's known? What Hamed proved is the even cycles and the complete bipartite graphs, and the hypercubes are weakly norming. Yeah, and there's actually a very nice way to see that these are norming, even stronger property, which is the diagonalization of your adjacency matrix. So if you think about the diagonalization of your adjacency matrix, then it's a symmetric matrix, and because it's symmetric, it has real eigenvalues. Yeah, and if you think about the standard effect in like undergrad graph theory, then the cycle count, your number of closed walks, right? Number of closed walks of length 2k is basically the sum of the 2kth power of your eigenvalues. Right? Yeah. And because I'm normalizing a little bit by dividing this by n to the 2k, so my C2k density in my G is actually something like this, mu1 up to mu n, where my mu I is lambda I divided by n. Yeah, because I'm dividing everything by n to the 2k. Okay? Yeah. So if I take the 1 over 2kth power of this, then it's basically the 2kth norm of your spectrum. Yeah, which is so-called Schatten norms in operator theory. Yeah, it's a fancy name, and yeah, there's another reason, so I'm selling another reason. So it's a generalization of Schatten norms in operator theory. Yeah, I can sell some functional analysis facts if you're interested in such a stuff, but probably you are discrete mathematicians, so I should move on to this topic. So this is what Hamed proved, and there are other properties he proved, which I'm going to mention later on. So let me just prove. Let me just list up some positive result, which means these graphs are weak norming first. Yeah, and then Lovas, in his book, The Large Graphs and Graph Limits, he proves that KTT minus a perfect matching is weak norming. So it's in chapter 14 of his book. Yes, just in case you look for the content. And chapter 14 is quite far away from the start. Yeah, so, yeah, and David Collin and myself prove that all the reflection graphs are weak norming. So these include all the known examples so far and adds many more. So to define these graphs, so we named this, we need some algebraic stuff. Like it's defined in terms of cosets or finite reflection groups, which takes some time to explain. So let me just give some brief examples. If you take n set, your favorite n set, and on one side you list up all the k subsets, and on the other side, say you list up all the r subsets, and you put an edge if an R set contains a K set. So let's say R is larger than K. Yeah. This is a bipartite incidence graph between R sets and K sets. And this is a reflection graph. Yeah, an example of reflection graph. And if you know what the regular polytopes are, then you can basically replace these K sets and R sets by some K faces and R faces of a regular polytope. Yeah. And there are like some, yeah, and it contains all the known examples and it adds many more. And we even conjecture that these are just all the weak norming graphs, which is kind of ultimate grand conjecture of ours. Yeah. So, yeah, but these are what's known for the positive side. And let me just mention.
You think that they are weakly norming?
Yeah, they're weakly norming, and we conjecture that the converse is also true.
Oh, all weakly norming?
Yeah, all weakly norming graphs are of this shape. Yeah. So.
What do you say about polytopes?
So take a regular polytope, and then you take basically the same. It's the K sets are the. I'm always confused with these indices, but over simplex, right? Yeah, and you basically replace your simplex by a regular polytope and the same holds. Yeah. Okay. And what's known for the negative side, which means these are not weak norming, or weakly norming graphs must satisfy this, and hence these are, and as a consequence, you can just rule out some non-weakly norming graphs, and so on. So these are what's known. So again, Ahmed Hatami proved that. So let me just say folklore. Any weakly norming graphs are bipartite. It's a bit overkill, but probably the cheapest way to see this is through this fact. So every weakly norming graph is Cerenko, and every Cerenko graph is bipartite. So every weakly norming graph is bipartite. Yeah, yeah. But it's a bit overkill. You can actually cook up some functions that breaks the triangle inequality if your H is non-bipartite. Yeah, that's not so difficult. But yeah, that's basically yeah. So every weakly norming graphs are bipartite. And what Hatami proved is the following. Firstly, it's every connected. So he didn't really mention this connectedness, which should be corrected. So connected weakly norming graph is one balanced, which means if you take the maximum over all f in H, where your number of edges divided by the number of vertices minus 1 is let's call this like one density or one average degree or whatever, then the maximum is attained by H itself. So you have no proper subgraph that has larger average degree. I mean, it's not really average degree, but you can actually prove the same statement in terms of average degree, and without assuming the connectedness. So if I delete connectedness here, then it's really the average degree. Yeah. Okay. And the second one is more interesting. So it must be biregular. So every weak norming graph must be biregular. By biregular, I mean, because it's a bipartite graph, there's some bipartition. And in the bipartition, on the same side, every vertex has the same degree. So this really rules out many graphs. Yeah. For example, the one example for a pseudo-Renko graph is the following. So if you have one vertex that's adjacent to all the others on the other side, then it's pseudo-Renko. And this graph is not biregular unless it's a complete bipartite graph. Yeah. So yeah, that gives you some example, an example that there exists on pseudo-Renko graph, which is not weak norming. Yeah, so these two are proved by Hatami, and recently, Dan Krot, Thaisa Martins, and Peter Pak, and Rokna, I forgot the first name because I've never met him. Yeah, proved that there exists non-weakly norming edge transitive graph. So it was actually a question by Hatami. So you could kind of see that every weakly norming graph is somewhat symmetric. Like here, every vertex has the same degree on the same side, and it doesn't really have like denser subgraph. So you can imagine that it's somewhat yeah. And if you look at these graphs, then all these are edge transitive graphs. So it's kind of a natural question to consider. And what they proved is there exists some non-weakly norming graph, which is basically this. You take some box product of even cycles, where your k is larger than 2. Yeah, by box product, I mean you take, so G is, so H product G is the graph on the Cartesian product of vertex sets, where your UV and U prime V prime are adjacent if one of them are equal and the others are adjacent, and or the other way around. Okay, and if you consider like C6 times C6, then it basically looks like a torus. So yeah, this torus of 6 cycles. So here you also have 6 cycle, and here also 6 cycle, and it looks like a torus. Yeah, and this is even a pseudo-Renko graph that's proved by David, myself, and John and Jungbom. So this is an edge transitive pseudo-Renko graph which is not weak norming. So yeah, this fails quite badly. Even if we assume some strong condition like edge transitivity, the converse doesn't hold. Okay. Yeah, so this is what was proved. And yeah, so I'm connecting this topic with to the pseudo-Renko's conjecture. And one very notorious example that remains open so far is this graph, K5 minus C10. So pseudo-Renko himself in early 90s asked that if this graph satisfies his conjecture or not. And so far, no, like, despite of loads of partial results on pseudo-Renko's conjecture, no one really managed to prove whether this guy satisfied the conjecture or not. So if the conjecture is true, then it should be true. Yeah, but yeah, we don't know yet. And what Hatami asked is whether this graph, this notorious graph, so this looks like this. So it's like a twisted 5-cycle. Yeah. So it's, because of that reason, it's sometimes called Möbius ladder. So there are a couple of ways to like look at this graph and think about Möbius strip. Yeah, but that's one way. And yeah, so Hatami asked if this graph possesses a strictly stronger property, which is weak norming. And it has been quite frustrating that we don't know how to answer that question for 10 years each. Yeah. And what I did with Bjarne is to answer that question. So this guy is not weakly norming. And so you can see here, Hamed proved that every cube graph is weak norming. So cube is 3-dimensional cube looks like this, obviously. So he also asked if some sort of same operation for a longer cycle also gives you a weak norming graph, which means this graph, whether this guy, the hexagonal column, yeah, this guy is also weak norming or not, and we answer that question too. So if you fully understood the definition here, then it's actually one edge times an even cycle. Yeah, so this is not weak norming either. So I have 20 minutes. So let me explain some rough ideas of our proof. Okay, yeah. So one thing quite beautiful about these graph norms, like weak norming graphs, is there are a bunch of equivalent ways to define it. So here's a theorem. So the following are equivalent. So firstly, my graph H is weak norming. And secondly, I'm going to write some seemingly complicated inequality. To that end, I should introduce some notation. So th of w, where my w is a vector of a function indexed by the edges of H. Don't be too scared. I'm going to explain it later on. But the definition is this. Whenever my edge E exists, I assign a different function for my edge E, which means the following: when my H is C4, for example, then there are basically 4 functions, W1 up to W4. So here's my, so just first edge, second edge, third edge, and so on. So what I'm going to do is to consider this W1 up to W4 as a graph that shares a vertex set. So there are 4 graphs that shares the same vertex set. Okay? Then I'm going to assign some colors. Like W1 is white and my W2 is yellow. So they're not necessarily disjoint. They can share some edges and so on. So this is W3 and that's W4. Yeah, something like this. And what I'm counting with this expression is a rainbow copy of 4 cycle. Yeah, which means the following. So my th of w is basically I'm counting the normalized number of my first edge being white, and the second edge being yellow, and the third one is blue, and the fourth one is red. So by this expression, I'm counting such a rainbow copies of 4 cycles. Okay? And the inequality is the following. My th of w is at most the product of the th of we. So this is the standard expression. And what I've taken here is the geometric mean of these guys. So what do I mean by these guys is, so for example, my 4 cycle count in my W1 is just a monochromatic copies of 4 cycles in the white color. Yeah. So if you think about this W1 as a white graph, then I'm just counting the white ones. And the W2 is obviously the yellow copies of 4 cycles. So what this product means is the geometric mean of monochromatic copies of my H. So I consider all the monochromatic copies of H in each color and count them and take a geometric mean. So it's some sort of correlation inequality. Okay? So this inequality is quite powerful. For example, I can prove this fact quite easily. So suppose my W E star for some fixed E star is some W, and for all the others, E other than E star, I just put 1. Okay? Then what I get for this guy over here is just the edge density. Right? So I don't care about the others, I just count. So this product here is just W. So here I have an edge density on the smaller side, and what's here is actually all the others are just 1, but the E star 1. So what I have on the right hand side is actually th of w to the 1 over AH. And this is exactly what Cerankos conjecture states. Yeah, so I can easily replace my G by this two-variable symmetric function in the limit setting. So if you believe that limit argument, then this is exactly what Cerankos conjecture tells. So yeah, by applying this inequality for possibly the simplest instance, we've got Cerankos conjecture. And I can generalize this to obtain the following. So it's easily generalized for to obtain such a statement, which is a very strong correlation inequality. This basically tells that my H count is somewhat larger than the F count. By larger, I mean if I scale down with the correct exponent, then it gets larger. So somehow the H count when H is weak norming really is maximized by H itself. Then it's proper subgraphs. Okay, so it's really a strong inequality, and yeah, it has lots of applications as well. And yeah, so this is a second one, and this equivalence is due to Hatami. And what we observed is a third one. So yeah, this has been implicitly appeared in the recent paper by Garbe, Jan Hladký, and yes, 3 more people in Prague, and yeah, let's say et al. Yeah, so yeah, but we had a little bit shorter proof, and which is more natural statement. So So if you think about the graph setting, the convex graph parameter makes no sense. But if you think about this two-variable function setting, then the convex parameter makes perfect sense because the vector space itself is a convex set. And I can define some convex function on a convex set. So by convex, I mean whenever I take the convex combination of two variable functions, then I have this. So here I should say convex for those functions, 0, 1 squared to 0, 1, because I need some non-negativity. Yeah. This looks quite natural because with a little bit of deception, actually, if the triangle inequality holds, then it immediately tells some convexity. So if I put lambda here, 1 minus lambda here, then I'll get lambda here, 1 minus lambda here. So this tells that my norm is convex, obviously. But my norm here and my h count is a little bit different because my norm here is the th to the 1 over the number of edges in h. Yeah. So it's a little bit different. So the convexity of this guy and convexity of this guy may be a little bit different, but it's not so hard to prove that these two are equivalent. So one direction is kind of obvious. If this is convex, then this is also convex because I'm taking some convex function here, which is x to the e to the h. So it's a composition of those two functions. This function is composition of those two functions, and hence I get convexity for this guy quite obviously. Yeah, and the converse is not so hard to prove. Yeah, so let me. Okay, I have maybe 5 minutes. So let me just explain how the proof works a little bit. So I can discretize the setting, which means so this being convex, if and only if this is convex for any step function. So which means, yeah, I assign some constant values for each square. Yeah, because it's a standard fact from like measure theory course. Yeah, every two-variable measure function is a limit of the step function, and you take dominate convergence theorem. Yeah, and so on. Okay. Yeah, so what I'm going to do is to consider 3 by 3 matrix. Yeah, and if I assign some variables, so this is a symmetric matrix because I'm considering some symmetric functions. So this is a symmetric matrix, and so on. And I can actually write down the h count in this particular 3 by 3 matrix or step function. Yeah, and that becomes EH degree homogeneous polynomial. Polynomial in 6 variables because I have 6 variables because it's symmetric. Yeah, so symmetric, so polynomial on 6 variables. And because it's convex, polynomial being convex is equivalent to your Hessian being positive semi-definite. Yeah, it's a standard fact from like undergrad calculus course. Yeah, so this is equivalent to, so let's say this polynomial is a P of H, then the Hessian is positive semi-definite. Yeah, and that's defined by the second derivatives of the polynomial for ij. Yeah, and by analyzing these Hessians, I can say that there's a point that my pH is not positive definite, which implies that my pH is not convex around that particular point, so that I can cook up a pair of two-variable functions that violate the triangle inequality. And that's how the proof worked. Well, we tried quite hard to find such an example, but that's basically the idea. So we prove that through analyzing the Hessians. Yeah. So yeah, let me just stop here.